Today we will start our third unit, that is a finite element method, or we can say finite element analysis of CAD/CAM and automation. So this is Professor N.S. Surner from Sanjeevani College of Engineering, Kopergaon. So syllabus of SPPU Pune is like this. So first one is the introduction. So in that there is a brief history of FEM, then finite element terminologies. So in that there are nodes, elements, domain, continuum, then degrees of freedom, loads and constraints, etc. Then general FEM procedure, applications of FEM in various fields, then meshing, then P and H formulation, advantages, disadvantages of FEM, and this is the only theory part. Then there is a one-dimensional problem. Now this is a actually numerical part. So finite element modeling, coordinate and linear shape functions, then assembly of global stiffness matrix, load vector, properties of stiffness matrix, finite element equations, temperature effects, etc. Now theory and numericals are composite shaft, then spring elements in series and parallel, then trusses, introduction, 2D truss, assembly of global stiffness matrix, and numerical limited to only 4x4 matrix. Okay, so this is about the syllabus. Now we will start off from the introduction. So what is FEM? FEM is nothing but the finite element method, or we can already say FEA. FEA is a finite element analysis. Now in FEA, we solve the problem by using software or by using hand calculations, right? So that is a approximate method. FEA is an approximate method which will give the approximate solution. Okay. Now what is the main characteristics is nothing but it can give the stress or the result at each and every point, or we can say at each and every node or the element, right? Because it define the equation for each element and then combine all elements equations, right, and then solve it. Okay, now what is the element, what is the node, so we will see later part, but just remember the procedure. So this is a problem statement, we can say, or the problem, then we do the sketch by hand, then CAD model, and then we solve the FEA, or we can say CAE. Okay, so this is about the general. Now what is the history? The term finite element was first coined by the clock in 1960. Okay, so in 1960 it was defined by the clock. In the early 1960, engineers used the method for approximate solutions of the problem in stress analysis, fluid flow, heat transfer and other areas. Okay, so in 1960 and early that engineers are only try to get the solutions of the complex problems of the stress analysis, fluid flow and heat transfer, right? The first book was written by Zenviquiz Weeks and the Chung, was published in 1967. Okay, so first book. So in that in the late 1960 and early 1970, the FEM was applied to widely variety of engineering problems, right? And after 1970s, actually FEM software packages are derived, right? So Abacus, Adina, ANSYS, Nastran, etc. So these softwares are derived to solve the complex problems, right? So in FEM we can solve simple problems by using the hand calculation, right? But to solve the complex problems or the huge problems, so there is a need of computers. Okay, so just solve the matrix. Okay, so matrix is the main problem. Now what advantage? So firstly we will see the advantages part. So it can readily handle very complex geometry. The heart and the power of FEM is nothing but to solve the complex problems, right? So simple problem, beam, truss, then plate, we can solve by using the hand calculation or the analytical method. But to solve the complex problems with having different shapes, size, huge problems, so FEM is a very useful procedure. Then can handle wide variety of engineering problems. So many types of problems. Okay, engineering problems, solid mechanics, fluid, then dynamics, electrostatics, heat problems, So many problems can be solved by using the FEA. Then can handle complex restraints, right, can be solved. Then can handle complex loading, right, different types of loading we can give, right. So many advantages of FEA. Now what are the disadvantages? So general closed form solutions which can permit one to examine system to response to change in various parameters. It is not a produced, right. Then FEM obtains only approximate solution. That is the first sentence of FEA. FEA is a approximate procedure, right. So we cannot get exact solution, right. Then FEM has a inherent errors, human errors, mistakes, right, depending on the human, so we can get the solutions, right. So these are the disadvantages. Now common FEA applications, now where we can solve the FEA problems, or we can apply the FEA procedure. So mechanical, aerospace, civil, automotive engineering, wide variety of engineerings, right, mechanical, aerospace, civil, automotive engineering, etc. Then structural stress analysis, structural, linear, non-linear, fluid flow, heat transfer, electromagnetic fields, soil mechanics, acoustics, biomechanics. These are the fields where we can apply FEA, right. Now methods for solution. Now just classification: analytical method, numerical method. In analytical, exact solution and approximate solution, right. Exact solution by using the Laplace transformation, separation of variables. These are the methods. And then approximate methods are Rayleigh-Reed's method, Galersin method. But in numerical solution and FEM also approximate method. Then numerical integration, and then finite difference. So these are the methods to find out the solutions. Now we will start with the discretization. So discretization means FEM is nothing but the finite element. Element is nothing but the one single division, right. So suppose there is an object in that so to solve that object by using the FEA, firstly we have to divide that object in number of small parts, right. So that is nothing but the discretization. Discretization is nothing but the dividing the object into number of, or the finite parts, right. So that's why finite element analysis, right. So finite element is nothing but the division or the part, okay. And that part is having, or that single division is called as an element, and to that element there are endpoints, and that endpoints or the points which are called as a node or the nodal points, right. So what are the types of elements, right. So in general studies there are 1D element, 2D element and 3D element. So these are the basic types. But in 1D element, depending on the application, right, 1D part, suppose there is a 1D part is a beam, okay. So for beam, so beam element is used, right. So for truss element, so for solving the truss, so truss element is by using the depending on the parts, so we can divide the 1D element also, right. So 1D object is there, so for 1D object we can use the 1D element. So 1D elements are spring, truss, beam, pipe, etc. So then there is a 2D, so plane element we can say, so membrane, plate, shell, etc. So for 2D parts, so 2D elements are used. And then lastly is a 3D element. So for 3D parts, so 3D element is used like tetrahedron, hexadron, brick elements. So these are the elements. So these are the nodes. So this is the nodes, this is also nodes. So this element is having two nodes and one, this is the element. So these are also nodes 1, 2, 3, 4. So see, this single element is having 4 nodes. So this is also element. So these are having 1, 2, 3, 4, 5, 6, 7, 8. 8 elements are there, right. Sorry, 8 nodes are there. So this is about the types of element. Now we can see here, so this is object to analyze. So if you divide it, these are the elements 1, 2 and 3, and at the end or in between there are nodes which are connect the two elements to each other. So you can see here also in the analysis software, so 1D element, 2D element and 3D element. Then types of loading. So different types of loadings are there used in the FEM. So first one is the body force. So body force is nothing but the distributed force per unit volume. So that is nothing but the body force. For example, self weight due to gravity. So that is one type of loading. Then there is another traction force. So traction force is nothing but the force per unit area, Newton per meter square. So for 1D problem, T is nothing but the force upon area into per perimeter of the area. For example, frictional force, viscous drag, surface shear, etc. And last one is a point load, concentrated load, that is Newton acting on at any point. So this is nothing but the point load. So boundary conditions are load and constraint. Now constraints is nothing but the by where that element is used or the application of that object. Depending on that, we have to constraint. Constraint is nothing but the restricting the degree of freedom of the part, or we can say the node or the element, right? Suppose there is a table. So table is holding, or the whole table is resting on the pillars, right, or the legs of the table. So to do the analysis of table, we have to fix the legs end part, right? So that means we have to fix, or we have to constrain the degree of freedom of the legs. Okay, so that is nothing but the constraint. Now what is the degree of freedom? So degree of freedom is nothing but the field of variable for a single point, right? How to calculate degree of freedom of that particular object is nothing but the formula is number of nodes, and the product of number of nodes means number of nodes multiply by the number of values of the field variable, or we can say simply number of nodes in that object multiply by the degree of freedom of a particular node, right? Then H and P refinement. Now meshing is nothing but the discretization. Meshing is nothing but dividing the component into number of element, right? If you divide number of element, if you divide that object into so many number of element, if that number of elements are higher, so there will be the higher refinement, right? If number of elements are lower, right, suppose one part is divided into only 5 element and same part is divided into 10 elements, so that 10 element part is having the more accurate solution than the 5 element, right? If you divide the element number of element count is more, then you can get a more accurate solution, right? So there are two types of refinement, H and P. Now what is the H and P? So H method is nothing, improves the result by using a finer mesh of the same type of element, right? Now you can see here, so this is the original mesh. If you refine by using H method, that means you are dividing or you are increasing the number of element of that object, right? So that is nothing but the H method. And another method is a P method. So P method improves the result by using the same mesh but increasing the displacement field of accuracy in each element. So this method refers to increasing the degree of highest complete polynomial. So that means the P, so same number of elements are there, but the degree of freedom of that element are used, increased, so that we can get the more accurate solution. So this is about the first part of our FEM. So next coming parts we can cover the remaining unit of FEM. So thank you.